Okay guys, welcome to lecture 4 on linear systems of equations and a BQP-complete problem. So this is for quantum complexity theory, the winter 2020 offering at Paderborn University. So last lecture, we took our time to really formally define the quantum analog of P, which we called the BQP. Okay, and remember, of course, in this course, that really means promised BQP. And when we think about BQP, like the algorithms or the problems we can solve in polynomial time on a quantum computer, typically the most famous examples which come to mind are Shor's factoring algorithm, of course, and Grover's unstructured search algorithm, let's say. Okay. But in the last decade or two, there's been another algorithm which is slowly kind of rising into these ranks, which is this very well-received algorithm by Harrow, Hasadim, and Lloyd, which is often just denoted the HHL algorithm. And it's an algorithm which, quote-unquote, solves systems of linear equations, and I'll tell you more about what that means today. And the algorithm especially has seen a lot of attention in the context of things like quantum machine learning, which has kind of arisen as a field of research in the last kind of 5 or so years, I would say, but perhaps even longer. Okay, so the quote atop today's lecture to get it started is by Wikipedia, okay? And basically what it highlights is that a lot of times in mathematics, the person something is named after was not necessarily invented by the person themselves. Okay, this happens way too frequently. And Gaussian elimination, which is one of the most natural algorithms we have for solving systems of linear equations, classically, that existed long before the person whom it's named after, which is Carl Friedrich Gauss. Okay? So the quote reads, "The method of Gaussian elimination appears in the Chinese mathematical text, Chapter 8, rectangular arrays of the 9 chapters on the mathematical art, ... Parts of it were written as early as approximately 150 BCE, ... Carl Friedrich Gauss in 1810 devised a notation for symmetric elimination that was adopted in the 19th century by professional hand computers to solve the normal equations of least squares problems. The algorithm that is taught in high school, presumably a Gaussian elimination, was named for Gauss only in the 1950s as a result of confusion over the history of the subject." Okay, so the idea of this elimination algorithm has existed, for 2,000 years, basically, right? But we call it Gaussian elimination. That's just the way the dice roll or the chips fall. I'm not sure which saying you want to use here. Another very famous example of this is the FFT, the fast Fourier transform, is typically credited to Cooley and Tukey, who gave, I think, the most recent and kind of well-popularized discovery of the algorithm. But the FFT itself was apparently known over a century earlier by, I think, Fourier himself. But I have to brush up on that trivia. Anyway, so today we are talking about systems of linear equations. So, very briefly, what do I mean by that? I basically mean systems of linear equations. And remember, what we really mean by that is that, I'm going to give you a system of equations of the form, AI1 x1 plus AI2 x2. Maybe I'll index them explicitly for the first time. ... plus AI capital N xn equals to b1. So that's the first equation. And then, I might have a list of these, right? So the last one in the list might be am1 x1 plus am2 x2 plus ... plus amn xn equals to bm. Okay? And of course, these are all going to be scalars, the ai's and the bi's. These are just complex numbers, let's say. These are your variables, the xi. So these guys, okay? And of course, the goal is to, find x1 through xn in complex n, satisfying all the equations. Okay, and so you have a list and you want to satisfy all of them. And kind of the most compact way to write this, so this thing here, if you want, what you could do is you could rewrite this as a times x equals to b. Okay, where Basically, x is a column vector. It just lists the variables one by one like this, right? Likewise for b, this is a column vector. And a is basically, you just kind of take this block and you remove the x's and, you start writing the coefficients one by one in a row, right? So a11, a12, up to ain, that's the first row, each entry in the first row, and so forth. So you get this big matrix A. So I'll let you kind of work that out as an exercise, just so you're comfortable. Okay, so what we want to find is, typically we'll think about it this way in this lecture, which is that I'm giving you a matrix A as input, an n by n matrix A, and a vector B, which is an n-dimensional column vector, and your goal is to find x satisfying this equality. Okay. Now, what we're going to do in this lecture, as the title suggests, is we're going to solve via a quantum algorithm, a system of linear equations. And this is going to work exponentially faster than possible classically, right? And in particular, we'll see that the algorithm will run in time in certain regimes, in time logarithmic or polylogarithmic in this dimension n. Okay, so you don't even need to write the full thing out. So of course, based on what I just said, I'm giving you an algorithm that takes, time exponentially smaller than what it would take to even just write out the solution. You should immediately kind of stop and take a moment and say, wait a second, what do you mean? Like, how can you solve a system without even taking the time necessary to write out the solution vector itself, right? Which would require order and time. Well, the answer is, we're cheating, right? I mean, we're not really solving the problem of solving a system of linear equations per se, which would normally require you to write out all of x. But rather, what we're going to do is we're going to solve a related problem, which is we're going to allow you to prepare a quantum version of the solution vector. Okay, so we won't get x written out in its entirety, but we'll get, the quantum state, which lives in, the space Cn, right? That only needs log n qubits to write down. And of course, given this quantum state, sorry, I'm not going to write it this way because that is not correct. What I mean to say is I'm going to write out, B1 through, x1 through xn, right? So this is more accurately what I meant to say. This is a quantum state psi, right? It's written in superposition. Okay, so the amplitudes are the xi, basically. And we're going to prepare that quantum state. And of course, given that quantum state, I cannot necessarily extract all the entries x1 through xn, because once I measure it, I destroy the state, right? So that's the catch. Of course, we're going to get an exponential speed up, but we're not really solving the same problem that a classical solver of the system would. Okay? So this is something you do need to keep in mind. Okay, and in the process of doing this, we'll see that a very natural BQP-complete problem arises, which is that of inverting a matrix. Okay, so that's the basic setup. And I think it goes without saying that solving systems of linear equations is kind of one of the most important tasks that's solved every day in a broad field of broad array of areas in engineering and so forth, technical areas. So it's very natural that we would want to solve this problem. Okay, so before I give you the actual algorithm, what I want to do is I want to take some time sketching the basic framework of the algorithm, because kind of behind the scenes is this very nice, simple, and very elegant framework that in principle applies to a wider class of problems than just solving linear systems of equations. So the basic idea, this is section 1, is what I'm going to call here quantum eigenvalue surgery, though this is not a standard term in the literature as far as I'm aware. Okay, and for that we're going to need 3 ingredients. Okay, the first is the quantum phase estimation algorithm. Oops. Okay, and this we'll review briefly in a couple of minutes. The second ingredient we'll need is a quantum Hamiltonian simulation algorithm. Okay, and that will also, I won't give you details of how it's done, but I'll state what it means to do that. And finally, we'll need a basic trick called pulse selection. Okay? So those are the three high-level ingredients we will need. Now, we are computer scientists, which means that we don't like to wave our hands, right? We like to be formal, and therefore I'm going to take a moment now to specify the exact problem that we're trying to solve. Okay, particularly because we're claiming to solve the usual problem of solving systems of linear equations with an exponential speedup, so we need to be very clear about what we mean about what exactly we're solving, because we're not even going to be giving ourselves time to write out the solution vector. Okay. So to state this problem specification, basically, I'm going to first remind you, of operator functions, right? Okay, so suppose you have a Hermitian operator, Hermitian matrix A. Remember, these are just high-dimensional generalizations of the real numbers, so the eigenvalues are all real. Okay, and you have a function f, which you want it to apply to a real number, and it should output a real number. So, for example, f of x could be something like x squared, or f of x could be x inverse, right, which is the one we're going to end up using today. Okay, and we are also given, so these are the things you're given, right? The third thing we're given is we're given a vector b. Okay, I haven't really specified what it means to be given this vector yet, but suppose we're, and maybe I'll try and keep this thing looking semi-classical, so I'll put that little twiddle sign to say that this is a vector, although I could have written a ket vector as well. Okay, and what is the goal? The goal of eigenvalue surgery, broadly speaking, right, is going to be to prepare f of a, right, so the function of a times b. Okay, and this is some vector in this space. Okay, so I know how to, I have b in my possession, and I want to prepare basically the quantum state corresponding to f of a times that. Okay, well, okay, that's in the quantum setting. Okay, so classically, the amount of time to prepare this answer, of course, will take omega n time. Okay, and why is that? Well, what does it mean to prepare this classically? Well, I mean, that means you're going to compute this vector, right? And that means you're going to write out the vector explicitly. And that has dimension n. So you're going to take at least omega n time, assuming all the components you're going to write with, say, constant precision. Okay? Now, suppose we change the, sorry, this is the classical setting. Maybe I should be a little bit more clear. This is in the classical setting, right now. And now let's change the rules of the game slightly so that, I'm not giving you, so that's, by the way, why I also wrote it as a squiggly b like this. So think of this as a classical vector right now. I explicitly wrote out the vector for you. But now in a quantum world, imagine I don't give you this vector as an explicit vector I wrote down, but as a quantum state. Okay? So quantumly. And of course, we're welcome to change the rules any way we like as long as it's reasonable and well motivated, and and so this is the way we'll choose to do it. Okay, so suppose we can let me give these guys bullet points. We can prepare now the quantum state ket b, and by that I don't mean well, okay, b is not a string, right? B is a vector, and so let me be very formal about what I mean by this. That means that I'm going to encode the amplitudes bi as coefficients. Okay? So remember, that's b over here is just equal to these b1 through bn, right? So those numbers are now your coefficients over here. Okay, and of course, this thing lives now, it's a quantum state, okay, it's a different object. It lives in an n-dimensional space, and that means that roughly we need order log n qubits to represent it. Okay, so we've already kind of gotten, we've compressed the space we're working in exponentially now. Okay, and so of course already you don't expect to be able to output now the full vector living in Cn at the end of the day. Okay. Okay, and so let me be clear also that we can prepare this thing efficiently. Okay, so in order to solve this problem, preparing B is not the bottleneck. Okay, that I can do. Okay, so the question is, how to simulate this operator now, f of a, quantumly, right? How do I apply that operator to a quantum state, ket B? Okay, so what I want you to do now is I want you to pause the video briefly and think about, hold on, right? What does it mean to even simulate f of a? What are the immediate kind of problems you recognize right away with even asking this question? Okay, so pause this video. I'm going to take a drink of tea. Okay, so I'm going to assume now you've unpaused. So what are some questions that arise, right, regarding trying to do this matrix multiplication task, right, quantumly on a quantum computer? Problems. Okay, and by the way, this is what you should always do. Like whenever you're faced with, you're trying to brainstorm, you're trying to solve something, you have an idea, right? You should always take a step back first and ask yourself at a high level, okay, are there immediate kind of red flags that I see, right? What is a high level view of the battleground, if you will, before you jump in, okay? So the first problem is that, number one, well, I'm saying I want to apply f of a to my quantum state B, but you remember in quantum mechanics, we're only allowed to play unitary operators, right? So who said f is even unitary? Right? It's not obvious at all. So problem number one, right? And so the idea here is that we're going to simulate f of a probabilistically. See via post selection. So remember I said one of the tools we'll need is post selection. Well, this is one place where it will play a role. Okay, so I cannot hope to do f of a deterministically because it's not unitary, but I can hope to do it by doing a measurement and then post selecting. Okay, that's problem number one. Number two, let's look at this vector, right? This thing over here, right? Sorry, and I defined, let me be a little bit more clear. Suppose now I want to prepare, let me just match the notes here. The vector x, which is literally going to be f of a times b. Okay, this is my goal. Sorry, I don't need a dot anymore, times b. Okay, so this is what I'm talking about. We're in the quantum world. By the way, let me take a moment to really stress that it is completely normal, and it does happen frequently that, in these video lectures, I'll make an error. When I'm discussing something, I'll only catch the error, much later after I've already released the video. So obviously there's no way I'm going to go back and fix it at this point. So usually what happens then is I'll update the notes, or the notes were correct, let's say, and I made an error. So do make sure you always check the notes along with the videos, right? And compare them. If you notice a discrepancy, the notes are what are correct, okay? The video is more or less live. I try to do minimal edits as I go along. Okay, so the other thing is that, this vector now, right? Right, who said, if this is a unit vector, right? But, so this is a unit vector. This thing is not necessarily unitary. So who said that, the output x is going to be a unit vector, right? And that's a problem, right? Because we're only allowed to have quantum states which are unit vectors by definition, right? The third one is that, so this matrix A, and hence f of A, essentially, let's start with A, right? The matrix A is exponentially large with respect to my number of qubits, right? I only have log of n qubits, right? That's what I wrote over here, right? I've only got log n qubits. But A is n by n, right? So I can't hope to write all of A down, right? A is n by n. But for us, efficient means poly in the number of qubits, right? And my number of qubits is log n. Okay, because that's the amount of space I needed to write down as a quantum state, to represent, as a quantum state B, okay, ket B. Okay, so I cannot write down A fully, so I'll need some form of succinct access to it. And I'll define this more formally later. Okay, otherwise there's no hope to solve this problem. Okay, and last but not least, the output of this algorithm, right? X is a quantum state. Okay, and so that means that I cannot read out all the entries or the amplitudes of X having prepared just one copy of X, right? So I can only hope to estimate kind of this expectation value X for any efficient quantum measurement M. Okay, so formally M could be like a projector or an element of a quantum measurement or a POVM or something like this, okay? So that's really all I could hope to do. I could estimate these expectation values of the solution vector X, okay? But I cannot extract all the entries of X. I don't have time to even do that. Okay, so that's going to be the problem specification essentially for this eigenvalue surgery at a high level, which we're going to then specialize to solve linear systems of equations, right? So we have X equal to f of a of X. This is what we want to do, and we have to deal with these problems. Okay, so what is the algorithm sketch? Okay. So I want to basically apply an operator function to A, right? That's what we're saying, f of A, right? And that means, remember, that I want to write, I want to compute some function of the eigenvalues of A, okay? And so obviously the first thing I should do for this eigenvalue surgery is let's just assume that A has spectral decomposition. A equals to the sum over J of lambda J, psi J, okay? So the lambda J are, of course, going to be the eigenvalues, and the psi J will be the eigenvectors. Okay, and let's just assume, for simplicity, for now, we'll fix this. Assume that, remember we wanted to solve, so this was our problem, right? We wanted to compute f of A times B, X, right? This was our goal. Okay. So this is the goal. Okay, so let's just assume for now that, you know, the B is going to be one of these eigenvectors psi J. Right? I don't really care which one, pick your favorite one. Okay? It's just going to make life a bit easier. So then what is our goal in this setting, right? The goal is to compute X, which equals to f of A times B, of course, which we just said is going to, I'm just assuming for now it's some eigenvector. And remember, by operator functions, this means that all we were really going to do here is we're going to apply the function to the jth eigenvalue and spit it out when we're given the jth eigenvector. Okay? So that's essentially the goal, right? That just means that kind of given the jth eigenvector, I want to hit it with a phase or an amplitude, basically. It's not necessarily a phase because it doesn't lie in the unit circle, but an amplitude, f of lambda j, that's it. That's what we want to do. Okay? So obviously, you know, if I'm given an eigenvector, right? And what I want to do is I want to produce some function of the corresponding eigenvalue, right? Then what basically we want to do is, you know, I want to use the eigenvector psi j to extract kind of lambda j out of the matrix A. And then I want to kind of manually apply the function f to that eigenvalue somehow. And then I kind of want to, you know, really wildly waving my hands here, I want to reinsert that eigenvalue back into the operator, okay, in its modified form. That's the very basic goal of eigenvalue surgery. Okay, so let me kind of break that down into steps, right? There's 3 steps. You extract the eigenvalue, you process the eigenvalue, and then you reinsert the eigenvalue. So let me be a little bit more precise about what I mean by each of these. So step 1, eigenvalue extraction. Okay, and this is where quantum phase estimation is going to come into play. And, you know, in this sketch, in the first section, I'm not going to define quantum phase estimation, but I will do that in a subsequent section of the lecture. Okay. Now, so what I want to do is I want to extract the eigenvalues of H, which are these lambda j. And so we have a problem, right? Problem is H is Hermitian, right? Not unitary. So I cannot implement H directly. Or I should guess, sorry. Keep thinking H because that's usually what we use for a Hamiltonian simulation. Okay, A is Hermitian. It's not unitary, so I cannot implement it directly as a unitary and then try and extract its eigenvalues. So I have to do something else. But the solution is simple, which is that, remember that U, okay, and I believe this was in the last question on your present assignment, right? If I take A and I exponentiate it, I apply this operator function, e to the ix, basically. This thing is unitary, okay? And what are the eigenvalues of this thing? Well, they're going to look very similar to those of A, right? They'll be e to the I lambda j. Okay, so remember these are just the eigenvalues, where was that? Over here, right? They're just the eigenvalues of H, of A, but because we applied an operator function, we just essentially exponentiated those. And the nice thing is that now this e to the IA is unitary. This I can implement. Okay, so what I need to do is somehow implement U, and using U, kind of take the phase that's hiding in the eigenvalues of U, and kind of take a log of that, kind of bring it down, so that I can extract lambda j itself. That's what I want to do. Okay, and anytime you have a number that's in a phase, like in an exponent, right, and you want to bring it down from the exponent quantumly, the first thing that should pop into your mind is quantum Fourier transform. Okay, that it has a tendency to do this kind of trick for you. Okay, and by using the quantum Fourier transform appropriately, that's exactly what quantum phase estimation accomplishes. It will bring down this lambda j from the exponent into a register that we can play with. Okay, and so in particular, quantum phase estimation, which, as I said, we'll review shortly. So for short, we'll just call this QPE in this lecture. What it will do the mapping for us. So using black box axis, and I'm waving my hand slightly here, but using black box axis to just this unitary U. Okay, so assume I can do U. It does the mapping, maps the jth eigenvector. Okay, so that's this, the jth eigenvector of H, or sorry, of A. It just maps it to, it leaves it invariant, but in a new register. And here, for example, maybe I have all zeros to start with. In that adjacent ancillary register, it will write out to the corresponding eigenvalue, lambda j, of the Hermitian operator A. Technically, it's the phase of the operator U, and that's why this is called the phase estimation algorithm, not the eigenvalue estimation algorithm. Okay, so if you want to know the eigenvalues of A given a copy of the eigenvector corresponding to the eigenvalue you want, then you exponentiate your Hermitian operator, and then you use phase estimation to rip out the eigenvalues out of the phase. Okay. So that's the very basic first part, that using phase estimation, right, I can extract the eigenvalue and I could store it kind of in a register, in this first register over here. Okay. And now step 2, once I have this eigenvalue stored in a classical register, now I can do whatever kind of classical computation I want on it coherently. Okay, like in superposition, I can do this. Okay, so now we just do eval processing. Okay, and we just apply the classical map. And this is not an entirely trivial statement, but whenever you have a classical reversible computation, you can always do this coherently, right? And you can always make classical computations reversible as well. Okay. Lambda j. So this is what we had, and now what we're going to do is we're going to map this to f of lambda j, right? So I apply the function on a new register. Again, I'm going to assume that maybe there's a 0 register here of ancillas. So I'm going to write the answer there. And these things don't change. Okay, so what's new is this part now. Okay, so in a new register on the side, I compute the function of the eigenvalue that I wanted. Okay, so now that I've completed step 2, I have f of lambda j sitting in a register. Now basically what I want to do is I want to take that processed eigenvalue and somehow reinsert it back into the operator A, whatever that means. Before I do that technically, so the last step I write down, step 3, is going to be that reinsertion step, but it's also going to need to clean up kind of any garbage we accumulated along the way. And kind of that garbage information right now is this register lambda j. I don't need the eigenvalues per se anymore, right? So step 3 technically is supposed to be eigenvalue reinsertion. Okay. And what do we want to do is, number 1, we want to uncompute. So number 1, we uncompute. So let's take f of lambda j psi j, right? And here, of course, you just run quantum phase estimation in reverse, basically. And that will undo for you 0, oops, psi j. So it eliminates this register. And now this register is 0, so I can I've reset it, basically, so I can essentially ignore it now and forget it. I can flush it down the toilet in the, I think in the great words of John Watrous. At least this is what I remember he used to say in lectures in Waterloo. But I could be wrong. This is just what my memory says. Okay, and so now that I have this, right, now I actually need to do the reinsertion step. And what does that mean? What I do is the following, right? I'm going to do a conditional rotation and then a measurement, right? Which means that I'm going to take f of lambda j and psi j, right? This is just what I had over here. Okay, and what I'm going to do is I'm going to add a new qubit, just a single qubit in this case, and I'm going to do this conditional rotation. The first 2 registers will not change, and maybe I'll write the new one in red, right? It's going to be something on 0 and 1, right? And ideally, what I want is, I want this to be the case. I want the number I want to kind of insert as an amplitude, right? Is going to be f of j. So by the way, note here that I have f of j sitting in a register, but that's not exactly what I wanted, right? My goal up here was I wanted to insert f of j as a scalar, right? As an amplitude in front and not sitting in a register. Okay? So this is a vector, and I wanted to multiply the whole vector by the scalar, essentially, right? That's not the same as what you see here, of course, because this is just like a bitwise representation of this value f of lambda j sitting in a separate register. It's not the same. Okay, so ideally what I want is this, right? I want to hit everything with this f of lambda j. And I can't do that because it's not a unitary operation. So what I do is I rotate a qubit up to f of lambda j. And in order to have some hope that this thing is normalized as a unit vector, of course I need to try and normalize it this way, right? F of 1 minus f squared of lambda j, okay? Okay, so that when I square and sum these 2 guys, they should sum to 1. It should be a unit vector, right? That's the basic idea, right? Of course, when you first stare at this, red flags should go up, right? It's not necessarily clear that, for example, that f of lambda j will be even between 0 and 1 itself, right? It could already be bigger than 1. Okay, we'll get to that later. But this is the basic high-level sketch, right? And so by the way, in the notes, I think I did things in the opposite order. I first did the conditional rotation and measurement, and then I uncomputed the garbage. That's fine. Here I'm doing it in this order. Okay, and now we basically post-select on 1 in the 3rd register. Right, so that means that this register over here, I'm going to measure that in the standard basis, and if I'm lucky, if I see the answer 1, I clap and I raise my hands and I say aha, right? Because I'll project this state down onto 1, right? That's what quantum mechanics said. And that means that this scalar here will stick around. It'll get kind of injected into the expression. Okay, so that means that if we're lucky, we measure 1, we'll get the state, the collapsed state, basically, f of lambda j, right, psi j. And here we'll have a 1 here now. I've killed off that superposition. But the nice thing is that this scalar term kind of floats to the front now, right? It's just a scalar. Okay, and now this is essentially garbage because it's just a classical register. I can uncompute that now. And so I'm left with basically essentially what I wanted, right? Oh, sorry. I guess I also wanted to compute this. Oh, that's why I did this in the last step, right? So technically, I still have a bit more garbage to uncompute, right? I don't have exactly what I want. So let's just do a sanity check. Right, let's go back up. I have, what I wanted was f of lambda j times psi j. And instead what I have is f of lambda j times psi j, but I also still have this f of lambda j sticking around. So, aha. Okay, so now I know the reason why I did everything in the different order in the course notes. What we really should have done is kept everything around up to this point, meaning that this step should kind of come later. Okay, so I should have kept around the f of lambda j, the lambda j, basically, and then psi j, right? I should have kept all that information around. And now that I still have lambda j, I can uncompute f of lambda j, right? I could basically compute it twice and do an XOR, if I want, for example, of each of the individual bits. So then I can map this to f of lambda j 0, lambda j, psi j. Okay, so this is just uncompute f, okay? And then I can apply my quantum phase estimation in reverse to get f of lambda j 0, and then that'll get rid of this lambda j term itself, and then I'll get this, right? And this is basically what I want, right? These are now have been reset to all zeros, so I can basically flush them down the toilet. And what I have is what I wanted, f of lambda j psi j. Okay, so that's the basic premise of eigenvalue surgery, right? We extract the eigenvalues out of the matrix using phase estimation. Of course, we simulate the matrix by exponentiating it into a unitary. Then we manually process all the eigenvalues to apply the function we want. And then we kind of reinsert them, quote unquote, via this post-selection trick. And we clean up the garbage. And the very last thing I want to say in this high-level overview is that we assumed, let's go back up for a second. We assumed over here that, where were we? We assumed over here that the target state was just an eigenvector, right? But what if more generally I don't have an eigenvector of A? Well, here we get really lucky because nature turns out to be linear. Quantum mechanics is linear, right? So as long as I can do it for each of the eigenvectors, and quantum phase estimation is defined with its action on that basis, right? I know exactly what quantum phase estimation will do on any linear combination of those eigenvectors. So I know what it's going to do on anything in the full space, right? So it's a general psi, right? Sorry, B, right? Then we can write, so since the evex psi j of A form a basis, right? We can always write, B equals to the sum over j equals to 1 up to n of some beta j, right? Whatever that is, right? For some coefficient beta j, which I don't need to know, frankly. And then our procedure that we sketched, what it will do is, by linearity, it will map this guy, sum over j equals to 1 up to n of beta j psi j. Assuming the post-selection works, of course, is going to map it to the sum over j equals 1 up to n, beta j, and then it will inject the phase you wanted. Okay, this is what you'll get. Okay, and then this is just nothing other than f of A times B, right? Whatever B was. Okay, so what I want to stress now is that I should it would be good to take a moment to understand why, when you go from here to the more general case, right? Why was uncomputing the garbage so important, right? This is exercise 4. Why is the uncomputing the garbage important? Not just useful, but important, right? So if I don't uncompute the garbage when I go from here to here, what breaks in the more general case? Why does this linearity argument not quite hold as is, right? And here, just think about the easiest way I like to explain this. Sorry, this should be a hint. Is think about the principle of deferred measurement. I mean, that's one way to kind of state the answer in the most succinct way possible. All right, so having talked about this notion of eigenvalue surgery as a very high-level framework for trying to apply an operator function f of a to a given quantum state, the technical tool we used there was, of course, the quantum phase estimation, or that was one of the tools. So let's review very briefly what that was all about. Okay, this is section 1.1 in the notes. So this is a review of the QFT, quantum Fourier transform, and QPE, quantum phase estimation. Okay. And if you want more details on these, you can go back to our previous course on an introduction to quantum computation that was taught in the previous semester, summer 2020. Look at the videos for that in the course notes. For now, I'm just going to remind you about the Fourier transform. And remember that, very roughly speaking, the Fourier transform, just as a mathematical transformation, is easily one of the most important transformations to engineering that has been discovered basically in the last centuries. So it's used in everything from like signal processing to make MP3 files possible to image segmentation, and even for fast multiplication of integers, right? So it kind of pops up all over the place. And basically, remember, the main thing the Fourier transform does intuitively is it kind of transforms you from the time domain to the frequency domain. So I can take a signal that's recorded in terms of time, and then it can kind of, process the information in that signal. So the x-axis now is labeled by frequencies rather than time steps. Okay, so then you could see exactly which frequencies show up in your signal. In the quantum Fourier transform, what is it? It's just the Fourier transform, which is a mathematical map, right? And it's a quantum implementation of that on a quantum computer. That's all it is. So in particular, the n-dimensional QFT, right? This is the way I'll refer to it. I'm just going to define it via its action on a standard basis for this discussion, and that's it. Remember, if I define a linear map on its action on any basis, then I know exactly how it's going to act on the full space. And so let me show you what it does to the jth standard basis vector, QFTn. You have some normalization. Okay, so it's 1 over root n, so the sum will have n terms in it intuitively, and we'll sum over all standard base states k. And here you're going to have e to the 2 pi I, and now there are two kind of important parameters here. Sorry, and let me do over n, that's kind of fixed as well. Right? And now the important parameters are j, and so as you can see, here's j, but that's where j comes from. It's the state you started with. And the other important parameter is k. And k is the one you're summing over. It's right here. Okay? So it takes, a fixed base state j and it scrambles you up into a superposition over all the basis states, the standard basis states, with these phases kind of injected. And the weights are uniform in the sense that the magnitudes are all 1 over root n, right? If these guys all have absolute value 1. Okay, so notice in particular what it's doing, right? I mentioned earlier that anytime you have say a phase that's hiding in an exponent and you want to bring it down, you want to think about trying the Fourier transform. And indeed, here's a number j, it's sitting in the ket, and indeed it's been lifted up here to the exponent into the phase. Okay? That's kind of the intuition. So I'm not going to give you the full circuit for that. It's not really important for this talk. The main thing is that kind of the naive implementation of the QFT requires naive implementation And by naive, I mean, of course, it's still non-trivial, but kind of the most basic quote-unquote non-trivial implementation requires something like order log squared n for, in our case, the number of qubits is log n, essentially, yeah? So the n is the dimension, so log of n is the number of qubits. So it's polynomial in the number of qubits is the key point, but it's exponentially faster than the dimension. Okay. So that's just the QFT. You know, I'm not going to state its definition. I'm sorry, anything more than the definition, because now when I state quantum phase estimation, you know, we're just going to plug in this definition and kind of be done with it, okay, for this lecture. So quantum phase estimation, very roughly speaking, remember, it's kind of like one of these tasks that seems perhaps useless up front, but it turns out to have surprisingly many applications, like all throughout quantum algorithms, so it's great. The basic idea is that, remember, as input, what are you given? Right, so imagine you have a black box access to cu to the k. So let me be clear what I mean by this. So u is just some unitary. Okay, so it's an n by capital N by n by capital N unitary. So exponential in the number of qubits is the dimension as usual. Okay, and the other thing you're given, oh sorry, let me explain what I mean by this, right? So this means that we're talking about the controlled version. And what I mean by that, in terms of this k here, that means that, you know, I'm going to have a register. Here's my u, right? And here, you know, I'll have a few wires technically, like I suppose I need log the maximum number k. And the point is that, you know, on these wires, you write k in binary, and then it will apply u to the k controlled on that number, right? So whatever number is encoded on this wire, like in binary, that's the number of times that u will get applied. Okay, that's what we mean by the controlled u to the k. Okay, so that's a non-trivial assumption, of course. I mean, especially when we start talking about the regime of k being larger than polynomial, right? I can always do this for k being polynomial with just polynomial overhead, but when k is super polynomial, in general, you cannot do this anymore, right? To raise a unitary u to really high powers is not going to happen for all u. Okay? Okay, and the other thing you're given is an eigenvector, psi j, of u, and it has an eigenvalue, e to the 2 pi I phi j, right? And we can assume without loss of generality that this phi j is between 0 and 1, right? Because otherwise we start wrapping around this unit circle, because the 2 pi over here. And the output is to compute so you have a parameter, right? So you get to pick this parameter. So maybe I should say you also get a parameter n, let's say. Okay, so we want to compute the n most significant digits of phi j, right? So this phase over here. This phase in general could be irrational, right? So the best I could hope for is some approximation to it, where I get to specify the approximation precision, the number of bits n, and WHP with high probability, right? High probability. That's kind of the goal of quantum phase estimation. Okay, so I think it's really worth taking a moment to remind you, and I've already said this, but this is exercise 6 in the notes, that access to, you know, cu to the k for k is in little omega of poly log n, right? So poly log n is polynomial in the number of qubits, right? That's efficient. So if you're going strictly bigger, your little omega of what's efficient in the number of qubits, then access to this thing is a non-trivial assumption. So in other words, you cannot do it for all such u efficiently. Okay, and here basically I ask you to prove that It's actually impossible. Well, it gives you a cute little exercise basically to show that in general we don't expect for you to be able to do this efficiently, to do this raising to high powers efficiently. And the idea is that you can, if you could do the search efficiently, then you can embed a brute force search algorithm for 3-sat to find a satisfying assignment that would run in polynomial time on a quantum computer. Okay, so but let me leave that to exercise 6 in the notes. So, in a nutshell, we do not expect, given an arbitrary u, I just give you black box access to u, that you should be able to compute, u to very high powers, k being exponentially large, efficiently. Okay. Now, in our setting, by the way, typically speaking, because we're talking about BQP, right, we only need a log number of bits of precision in phase estimation, right? Because then you get an additive 1 over polynomial error in your acceptance probabilities in some sense. And that's good enough for BQP, right? In BQP, we defined the acceptance, the completeness and soundness parameters so that they would be 1 over poly separated. So as long as your additive error throughout your computation is 1 over polynomial, you're generally fine. And 1 over polynomial additive error means a log number of bits of precision. Okay, so QPE itself is sufficiently simple that I could just write down the definition of the algorithm, assuming we're taking the QFT for granted. So let me just remind you how this goes. So you start with some initial state, eta naught in the notes, and you have some number of zeros, and this is where you're going to store the phase ultimately. And this is your eigenvector, right, evac. And this number t is carefully chosen, right? This one here. This is carefully chosen. It looks like this, n plus the log of 2 plus 1 over 2 epsilon. Okay, and what are these parameters you're seeing here, right? N is the desired precision. Let me just write this out. Right, so remember the output is to compute the n most significant digits of the phase, and so the bigger n is, the more space you're going to need in this ancilla. And epsilon here is your probability of success for phase estimation, what you're looking for. Okay. Now, so you start with this, right? And what you do is you apply, well, maybe I should, fine, let's just write it explicitly. We write H tensor n, right? So apply Hadamard's to this first register right here. And so what we'll get is, we'll get the state eta 1, which I'm defining as 1 over just an equal superposition of everything in the first register, okay, because I started with all zeros and I just applied Hadamard's. And there are 2 to the t possible strings in this register. Okay, so that's just that. And now I just leave this, so this is the part that's changed, and the eigenvector, of course, is just hanging around. And now, remember I assumed that, what have I used so far, right? So far I've used my eigenvector, right, there it is. I started with this in the first round. I've used n, right, that dictated over here how big my ancilla had to be initialized to. And the only thing I haven't used yet is my black box access to this controlled u to the k operator. So, I have an equal superposition over all k, so now it's just begging to have this controlled u to the k applied, right, for different values of k. So let's do that. Okay, so apply controlled u to the k with register 1 as the control. Okay, that's this one, right? And register 2 as the target. Okay, and register 2 is this one. Okay. So what do we get? So then we will get eta 2, right, equals the sum over, sum doesn't change, right? Okay, and so here I have a k. And remember that psi j is an eigenvector of u, right? So if I hit it with u, it'll pop out an eigenvalue. If I hit it with u squared, it'll pop out the square of that eigenvalue. And so if I hit it with uk, it will pop out that eigenvalue to the power k. And indeed, we'll get precisely this. We'll get e. Remember, the eigenvalues of u are going to be this, e to the 2 pi I. Here's my k. Okay. And then phi j. Right? Okay, so I'm assuming, let me just remind you, right, that psi j is an eigenvector of my unitary with this eigenvalue, right, with phi j in the phase. And so here I get exactly that eigenvalue, but to the power k, because I applied u to the power k. Okay, so that's what happens after I apply the controlled phase. And now we're almost done, right? I have something, what I want is this phi j, right? And remember, I have something in a phase, I want to bring it down out of the phase, q of t, right? That's the first thing you should think about, see if it will do the job for you. And if you look at the q of t, it'll basically show you that if I have an expression of this form, and I apply now the inverse q of t, essentially, it will bring this phi j back down. So let me just remind you what that looked like, right? So we had an expression exactly like this, right? We said that if I start with j, then it will map it to this kind of superposition where j is up here. And so now what we have below is we have literally this, and we want to go backwards to get this, and that's just q of t inverse. Okay? And apply q of t 2 to the t inverse, or dagger, basically, to recover a to 3 equals, technically the way it'll work out is you'll get 2 to the t times phi j, because phi j is a number between 0 and 1, so we kind of shift it over by multiplying by 2 to the t, so it'll be a binary string with the value bigger than 1. That's just a formality. Okay, so this is basically what it will compute. This is assuming that phi j is exactly representable in n bits. Okay, so if it turns out that, you know, phi j, this phase, the one from the unitary, right, this one over here, if that was representable using your parameter n bits exactly, right, then, you know, all of this is deterministic. Basically, you'll run the computation. After the q of t, you'll get precisely this quantity here, and that will be the end of the game. This will work perfectly, meaning with certainty. More generally, of course, phi j, you don't know what it is ahead of time, and it could require an infinite number of digits to express perfectly. And so then, you know, you could still analyze the q of t to see that with high probability, it will still, when you measure this register, it will still give you an estimate of phi j with good probability to within your desired precision n. Okay, so I'm not going to mention that because, you know, it's not really relevant for our discussion. So I can be a little bit more precise, meaning that if phi j requires more than n bits to write down, then choosing basically, in general, if you choose t equals to n plus p, right, so the size of that ancilla space, if you choose it to be n plus some extra p, right, implies that your failure probability of when you measure this first register, right, and getting kind of the n most significant bits of phi j to extract n most significant bits of phi j is less than or equal to, let's see, 1 over 2 times 2 to the p minus 1. Okay, so as you kind of might expect, you know, the bigger you make t, the more kind of the larger the ancilla space you have in which you can make an error, right? The better your probability of succeeding gets. This error probability goes down exponentially. Okay. So that's the very basic sketch for the q of t. Let me be clear that, of course, in general for the q of t, if you really wanted, like let's go back up here, right? If n is large, right, the number of bits of precision you want is, say, polynomial in the number of qubits, then t is going to be polynomial in the number of qubits. And then if I go to the sum here, right, the largest value of k I can get will be, 2 to the t, and in that case it would be 2 to the number of qubits roughly, and that's bad, right? That would be an exponential, k would be exponentially large in the number of qubits, and that means that I would need to apply this controlled u to the k for k being exponential in the number of qubits. It would be huge. And in general, we cannot do this efficiently. So always be careful when you do phase estimation. You can get log bits of precision in polytime, no problem. If you want to get beyond log bits of precision, you have to be careful. You can do it for some unitaries, like in Shor's factoring algorithm, you can do it to very high powers. But in general, you cannot do it for arbitrary u. Okay. And one other comment, exercise 8, right? So when I sketched the quantum phase estimation here, I assumed that the state I'm applying to is, I started with this state, right? Where I knew one of the eigenvectors ahead of time. But of course, there's a question of when I'm running an algorithm for some other task, right? And now I want to use phase estimation as a subroutine. I have no idea what the eigenvectors of my unitary are, right? I don't know how to prepare them. And again, this is exactly the kind of thing you see in Shor's algorithm. But nevertheless, the quantum mechanics is linear, right? We catch or break, right? So even if I have a state which is not an eigenvector exactly, but it's a superposition over eigenvectors, okay? Then, by linearity, this algorithm will apply exactly the same. It's just that each eigenvector will be tagged with its corresponding phase. Okay, so basically what you want to do is you want to show that if you take some state psi and apply QPE to it, where, and I'm really fudging notation here, by the way. So I have some alpha I, and it's just some superposition over all those eigenvectors, psi I, these are the evex. Then what it will produce basically is the sum over I, alpha I, and the corresponding phase, phi I, like this. So it'll do it in superposition rather than just having, normally in our expression above we didn't have this term, we just had phi I tensor psi I, and now it will do it all coherently in superposition. That's all I want to say about quantum phase estimation. Okay, that means we are now at section 2, which is we can finally talk about. So we set up this framework for using eigenvalue surgery, right? To do that, we needed quantum phase estimation, which we also reviewed. And so now we can talk about the actual quantum algorithm for linear systems. Quantum, so section 2. Quantum algorithm for linear systems. Now, so the basic idea is that, remember our goal was we were given AX equals to B, where, sorry, let me be a little bit more accurate, right? So remember that we're given A and B, right? And so this is just going to be some Hermitian operator. Okay, it doesn't have to be Hermitian, but let's assume it's Hermitian. You can still make the algorithm work in general. And let's suppose that B is just some vector in C to the n, right? And the goal was what? Is you want to compute the quantum state X, right? Sorry, quantum state X such that the matrix A times X as a quantum state equals to B encoded as a quantum state, right? Which is remember B, the way we defined B was we just took a sum over all I. We put equals 1 up to n, right? 1 over square root n. Sorry, I should say 0 up to n minus 1. Here we put I, and then here we put bi. That was the idea. Okay. And remember from basic linear algebra that whenever you have a system like this, the system has a unique solution if and only if A is invertible, right? So, and in that case, you would have A inverse B, assuming A inverse exists. Okay. And this is kind of the setting we'll use. We'll assume in our discussion here, we'll assume that A is Hermitian. We'll assume that it's full rank and hence invertible. you can generalize the algorithm to work even when the matrix is not invertible. Then you can do something called the Moore-Penrose pseudo-inverse. And all that really says, it's a very fancy way of just saying you're still going to invert the matrix just as you normally would, except you're only going to invert it on its support, basically, the space where it doesn't have zero eigenvalues, right? Because on a zero, you can't invert a zero eigenvalue. Obviously, then you'll get 1 over 0, which is infinity. But you could still invert this matrix on the rest of the space. And that's what the Moore-Penrose pseudo-inverse essentially does. Okay, so this is really, sorry, I should have put a cat here. So we want to apply this operator function, right? And we want to use Eigenvalue Surgery. And so really what we have is an operator function, f of x equals x to the minus 1, right? That's really what's happening. And so let me be very clear about this. Why is this true, right? What is A inverse, right? A inverse is just you take A and you invert all the eigenvalues of A, right? It's just, again, an operator function. I've applied this to the matrix A. That's what A inverse is. Okay, so the goal here is, if I want to affect, suppose I can, I have some way of implementing A, let's just say. Then I do phase estimation to extract the eigenvalues of A. I manually invert those eigenvalues. I do, x to the minus 1. And then I kind of stick them back in to hopefully affect this A to the minus 1B transformation. That's kind of the high-level overview. Okay, so before I show that, there are some things we have to discuss. And in particular, anytime you talk about linear systems, solving linear systems, there is a quantity which really needs to be discussed, both classically and quantumly. That is the condition number of a matrix. That's section 2.1. Condition numbers of matrices. Okay, so the problem is this. Even classically, right, if I want to invert a matrix, I want to compute, given A, I want to compute A inverse. Even if A is is full rank, so therefore certainly it has an inverse, it doesn't mean that in practice you can compute the inverse reliably. Okay? In particular, it turns out that certain matrices, those especially which have very high condition numbers, they're very what we call ill-conditioned, right? Which basically means that the inversion algorithm will be extremely sensitive to any sort of error. Like, so if you make any small error during the calculation, your final answer could be just way off for the inverse. And how far off are you? Well, that's precisely what the condition number is trying to capture, okay, in a number. So let me kind of motivate the setup, and then we'll define the condition number. So, so the basic idea is this, right? Suppose, I'm trying to compute, A inverse times some input matrix vector B. Okay, so and again, I'm not writing as a ket because, this is something that even applies classically. So I want to compute A inverse B, and I only know what A is, right? I don't know what A inverse is. So given A and B, right? Now, suppose, for example, I cannot even express B exactly, right? B is coming from the complex numbers, and I have a regular, normal laptop that exists in this world, meaning that it has only finite resources, right? So in general, it's not going to be able to represent numbers arbitrarily, like irrational numbers, right? So suppose we can only encode not B itself, but rather some kind of B prime, which is the true vector B, up to some error epsilon. And you should think of this as, it's just some error vector, error vector in C to the n. Okay, so it's just some kind of small fudge factor. Okay, because I have to truncate those real numbers at some finite precision, right, in the vector B. And now the question is this: how does A inverse of B prime, right? So B, and here's the prime. Let me really stress that, right? Compare. So if I take in my messy B prime, how does it compare with really the one I wanted, right? The one without the prime, the non-noisy version. Okay? And, well, what is this thing? let's have a quick look at this, right? A inverse B prime, by definition, that's just A inverse, right, times the original B plus the error epsilon, right? That was just this definition up here. So this is A inverse B plus A inverse times my error epsilon, right? That's just straightforward expansion. Now, this is the correct answer, and this is my error, right? And so if I'm trying to kind of get a sense of how important or how nasty the error is going to be for my computation, well, I just need to look at the ratio between these two, right? If the answer here is very, very large compared to this error, then, you know, I'm in pretty good shape, right? Because I'm not really going to notice this error much. But if it turns out that, you know, the answer and the error, like these two terms, can be roughly the same in value, then that's pretty bad, right? Then my error is huge, basically. And that's precisely what the condition number is trying to capture, okay? In particular, what we're going to do is we're going to look at the ratio between these two to see, you know, are they roughly the same or are they very different? And of course, we have to do this in the worst case, over all different choices of epsilon and b, right? You fix the matrix A, the condition number will be defined just given A alone, and the worst case optimization will be over all the possible vectors b and epsilon you can care about. So here's what we'll look at. I'm going to look at this ratio, as I said. So this is a vector, right? It's a matrix A inverse times epsilon. I'm going to take a 2 norm, right? So how long is that vector relative to A inverse of B? And, you know, stare at this for a second, right? These are precisely these two terms over here, right? This is this one, right? And this is the other one, right? So let's see, are those guys roughly balanced, or is one much bigger than the other? What's going on? Now you have to be just a touch careful, right? Because you also care, of course, I mean, this isn't really a fair comparison if, you know, the epsilon vector itself happens to be very, very tiny in length, right? Then, you know, no surprise that this thing will be very small to this one, right? We kind of have to renormalize things so that, you know, b and epsilon have roughly the same length, so that it's a fair comparison. We're comparing apples to apples, if you will. And that's essentially why you're going to see this other term that we plug in here to make sure that everything is nicely normalized. Okay? So this is the ratio we care about. And now I'm just going to reshuffle things around. In particular, there's an epsilon here and there's an epsilon here, right? So let me put those ones together. So A inverse of epsilon 2 over epsilon 2 times, and here I have a b there and I have a b as well. So let me put those ones together. Okay. And now stare at this for a second and see if you can, you know, pause the video if you like and see if you can tell me what this is. What is this really? We've already seen this quantity. Well, let me be clear. This is if I maximize this this thing here, overall epsilon. Right? So in particular, right, what I'm doing is I'm trying to understand what is this maximum ratio, right? In the absolute worst case for me is when this ratio is big, right? The error is huge compared to the right answer. Then the error will be very noticeable. So how do I maximize this expression? Well, you know, here I want to maximize this, right? This norm here, and I want to minimize this one, if you will. Okay? So what is this maximum here? Stare at this long enough. Okay, so this thing here is just, I'm just going to give you this definition, right? Remember that if I take the max over all psi of, you know, m times psi, and I renormalize by psi, this is nothing other than the spectral norm of m. Okay, we've seen this definition slightly differently before. When I first gave you this definition, remember the infinity norm? The goal is you're trying to see how much can a matrix stretch a vector. That's what this is doing. I explicitly wrote that the optimization is over unit vectors, but here I've dropped the unit vector part, and instead I just chose to renormalize the vector explicitly. Same thing. So this thing here, what is this? This thing is going to be upper bounded, right, if I upper bound, if I maximize over all epsilon, right, this is going to be at most the infinity norm of A inverse, right? This is coming from a maximization over that, over all epsilon. And now for the second term, it turns out that if I want to minimize this ratio, then I'm going to get an infinity norm again. And if you look at it long enough, you'll see that really what you get is this. You get the infinity norm of A coming out. Okay, if you minimize that expression. Okay, so you're minimizing the denominator, of course, so that the whole thing will be maximized. Okay, and notice how this used to have an inverse and this one does not, right? But this one used to be in the denominator and this one is not, right? So obviously those two things are going to play with each other. So I'll let you think about why that holds. Okay, and this is precisely our condition number. And the terminology that's typically used is kappa of A. Okay, so whenever I write kappa of A, I mean the product of the largest singular value, that's the infinity norm of A, times the times the smallest, I guess 1 over the smallest singular value, right? So technically, I'll write this more accurately in a second, but technically the infinity norm of A times the infinity norm of A inverse. And when A is Hermitian, then remember that the infinity norm is just the largest singular value of A. And we said in a previous lecture that if a matrix is Hermitian, then the singular values are just the absolute values of the eigenvalues. Okay? Then I could rewrite this, right? Then I could write, in this case, I could write everything in terms of eigenvalues, which is a bit nicer. Kappa of A is what? Well, it's, I'll just write it out. I'll let you verify for yourself that this is correct. So it's the maximum over all I of lambda I of A. Okay, so it's the largest eigenvalue in magnitude over the minimum, right? Over all. Okay? So this is really what the condition number is measuring. It takes basically the largest eigenvalue. Like if all the eigenvalues are positive, you can forget about this absolute value sign. It's looking at the ratio of the largest eigenvalue to the minimum, to the smallest eigenvalue. Okay, so if you, for example, and okay, let's see why this might affect your ability to invert a matrix, right? Just as a very quick sanity check, right? Suppose I had a matrix which had a 0 eigenvalue, right? The top eigenvalue was, say, 100. Okay, so A maybe looks like this. Here's my matrix, right? It's 100 and 0, right? The eigenvalues are 100 and 0. They're on the diagonal. Then, and this is a positive semi-definite matrix. Then the condition number is what? It's, well, 100 over 0, right? Ha. That's not good, right? That's a very high condition number. Right, and that's exactly what we expect because A is not invertible, right? It's rank deficient. It's got a 0 eigenvalue, right? So this thing captures exactly what we want. And at the same time, if I replace this with some teeny tiny epsilon, not 0, but I make the smaller eigenvalue just a bit above 0, then here, I'm going to get that tiny epsilon, right? And if epsilon is very small, then 1 over epsilon will be very big, right? So you'll get 1 over epsilon times 100. And this will be very big, right? So it's very nice because kind of the closer you get to 0 on that minimum eigenvalue, the larger the condition number will get. And so the harder and harder it will be to invert this matrix reliably without having the error causing you big time headaches. Okay, so in other words, in closing, this condition number is a single number. It's the ratio for our setting, because A will be positive semi-definite in our setting. It will be the ratio of the largest eigenvalue of A to the smallest eigenvalue. And the bigger the condition number is, the more sensitive any inversion process of our matrix will be to errors in encoding the input vector B. Okay? And for us, what we'll see is that it's going to show up in the runtime of the linear systems algorithm, right? So this kappa of A will show up there. That's not surprising at all, right? Classically, it's also going to be an issue. Okay, so just as a good sanity check, I already did some exercises here, but exercise 11 says that what is kappa of A for unitary A? Okay, so I encourage you to pause the video right now and see if you could figure this out. Just a cute exercise. And exercise 12, well, okay, I've already done exercise 12. It's basically asking what happens if A is ranked efficient, and I've already done that example. So this is kind of like exercise 12 in the notes here. Okay. So now we are ready to not state the algorithm yet. We've talked about condition matrices, condition numbers and matrices. Now, anytime anybody makes any claim about anything, but especially about quantum algorithms for something, you need to sit back and ask, okay, what are the assumptions that are going into your algorithm? Okay, because quantum mechanics is quite a highly structured theory. And generally speaking, it's not easy to design a quantum algorithm that just solves arbitrary problem of interest with a big speed up or something, right? It doesn't work that way. It's very nuanced, right? And so a lot of times, if you really want to get a very strong speed up, you really have to make certain assumptions about the setup, okay? Luckily, this is not true for Shor's algorithm, by the way. In Shor's algorithm, it works perfectly, right, for solving factoring. But in many settings like this one, we have to be very clear about the assumptions regarding when the algorithm will indeed give you a speed up over kind of a similar task classically. So that's why I have a whole section here for assumptions that go into the algorithm, okay? So throughout, I'm going to assume that A is Hermitian. In fact, I'm going to assume it's PSD in a second, positive. But in this section, this is what I write. And full rank, so it's indeed going to be invertible. And these can be relaxed, right? So the algorithm will even work, for example, if you're not full rank and you want to compute a pseudo-inverse. That's fine too. We won't do it in this lecture. I'm assuming that we have an efficient circuit preparing, remember, B. Okay, and this I'm just going to treat as a black box. I don't need to know anything about how the circuit works. And now remember, what I wanted to do is I wanted to prepare A inverse of B, right? And in order to apply this operator function A, f of x equals to x to the minus 1 to A, I had to use, I had to basically embed A, which is not unitary, into e to the IA, into a unitary, and then do phase estimation on it, right? So how do I do that embedding, right? How do we run something like e to the IA, right? I want to simulate that, because it is unitary. Well, for that, you need a Hamiltonian simulation algorithm, and that's the other assumption. So I need an efficient Hamiltonian simulation algorithm to implement e to the IA t, and t is just some evolution time. I mean, we can set it as we like, okay? And let me be clear here that, for both of these things, when I say efficient, right, I mean a polylog of the dimension n, okay? So the number of qubits is a log of capital N, right? N is the dimension, not the number of qubits. Okay, so in general, by the way, this is highly, highly non-trivial. Like this idea that, given any Hermitian matrix A, I can do this Hamiltonian simulation efficiently, you cannot do it in general. Okay, so that's exercise 13. That gets you to argue via basic counting argument that you cannot hope for an arbitrary U, unitary U, to always have some efficient simulation of it. Okay? Okay, now, luckily for us, okay, so this is impossible in general, and in fact, it's impossible for most Hamiltonians. Okay, and the basic reason why is because there's this nice isomorphism, right, between e to the IAT operated in that form, and so unitaries basically, and Hermitian operators A, right? You can go back and forth between the two pictures, and there are way too many unitaries on n qubits to be able to represent them all using polynomially many 1 and 2 qubit gates. Okay, just a simple counting argument will show you that. And so because there's this isomorphism between unitaries and Hermitian operators, this in turn means that you cannot simulate all Hermitian operators using short circuits, because you could always convert it to a unitary and then get a lower bound from the fact that most unitaries don't have a short circuit. So it's impossible in general, and in fact it's impossible for most Hamiltonians H, but there are some fairly broad class of Hamiltonians for which we can do the evolution efficiently. And indeed, these include, for example, the types of Hamiltonians we see in nature, which are local Hamiltonians. But that's not so important for this discussion here. What is important is that we can do it for something called S-sparse Hamiltonians. Sparse Hamiltonians. And sorry, I'm using the word A for us is Hermitian, right, in general. And any Hermitian operator can be thought of as a Hamiltonian. And a Hamiltonian is just a fancy way of, I guess, referring to a Hermitian matrix, but in the context of quantum mechanics, where a Hamiltonian operator, well, okay, maybe I'm debating whether or not I should make an attempt at writing down the Schrödinger equation, right? If you have a quantum state psi, right, and you want to look at its rate of change in time, it always equals to, some, I think there's an I in here, and probably like a T in here, and so it always evolves according to some unitary, and that unitary has some corresponding Hamiltonian operator H here, basically. It's just some Hermitian operator. So you don't need to know the Schrödinger equation for this course. I'm not trying to turn you into a physicist. I'm just trying to give you some sense as to why in the world I'm calling this thing a Hamiltonian. It's just a Hermitian operator, okay? And we can simulate that Hermitian operator by embedding it into a unitary. That's the idea. So we can do it as long as A is S-sparse, and let me tell you what that means, right? What does S-sparse mean? Two properties. So number one, there are less than or equal to S non-zero entries per row. Okay, and for us, typically, when I say you can do it, I mean that S is going to be polynomial here, right? More accurately, polylog in the dimension n. Okay, so a polynomial in the number of qubits. So basically, most of this matrix is going to be, well, in each row, most of the entries are zeros. Okay, but you don't necessarily. Many of the columns, of course, can have, well, let me not say it that way, but in each row, most of the entries are zeros. And number two is that there exists a polytime Turing machine, which, given a row index R, right? So you tell me which row you want, outputs the list of non-zero entries of A in row R. Okay, so not only are we guaranteed that the rows themselves are sparse, there aren't too many non-zero entries, but given any row I want, there's always some way to efficiently give me a list of all the non-zero entries in that row. Okay, and of course you tell me which index they're at as well. Okay, and of course that's important because if I don't know where in a row the non-zero entries are, then basically I'm kind of helpless, right? Because there are exponentially many entries, and only polynomially many of them are non-zero. How in the world am I going to find those, right? So we're going to assume that you have to also be row computable in this fashion. Okay, that's crucial. Okay, so if you're S-sparse, then the runtime you get, right, for S-sparse Hamiltonians, you can simulate e to the IAT with error at most epsilon sum h, and maybe this is with respect to trace distance, okay, with respect to the trace norm, okay? Remember, that's an important norm because then you can't distinguish whether or not you did the right computation versus the error the error computation, let's say, with a measurement. Okay, and so this is now in time O tilde log n. Okay, so basically number of qubits, and then S, which is the sparsity, and finally T, right, which is the time of the evolution. Oh, sorry, there's a square here. Okay. By the way, tilde means we're hiding usually log factors, but generally speaking, slower growing factors. So if I have this expression here times the log of s, then I'm just not going to bother writing that down for simplicity. Okay, so for example, I don't know if this is still the kind of the best running time, but certainly you can do it within this time, which is efficient. Okay, so it's polynomial in the number of qubits is the main thing, and it scales polynomial in the sparsity, right? So if your matrix is not sparse, it has exponentially many rows per entry, then this term blows up. Of course, you're in trouble. And by the way, let me be clear that this runtime I've written here, it's been simplified. It's really a more nasty expression, but I've used the fact that in our setup, I'm going to assume that the norm of A is 1. I think I skipped that, didn't I? I don't remember stating that. So before I write that down, so Hamiltonian simulation, if we have an S-sparse matrix, A, we can do it basically in polytime in the number of qubits. Okay, I didn't miss it, so let me write it down now. Okay, so we're talking about assumptions, right? And the last assumption, which is quick to state, and I've basically stated it, which is that I'm going to assume that the largest eigenvalue of this matrix in absolute value is 1. And basically, if you stare at this long enough, you'll see that basically this means, by definition, remember this condition number was what? It was this times this, right? And so we'll just get that this is, the condition number is just the infinity norm of A inverse. Okay? So it'll be 1 over the smallest eigenvalue if A is positive. Okay, so this is just going to simplify, but in general you can relax, you can certainly relax this assumption. Right? The ones about Hamiltonian simulation, those are a bit harder to relax, right? Because if you can't do Hamiltonian simulation, then the technique just doesn't work. You can't extract the eigenvalues out of your matrix using phase estimation, and so you're in trouble. Okay, we are now ready to talk about the algorithm itself. Woohoo, right? Can I draw a happy face? Very poorly. All right. So I'm going to make, just for the purposes of, to make the kind of the analysis simpler and to really make sure that the key ideas come through, I'm going to make some other assumptions. But these are less so, these are more about our analysis rather than the actual when the algorithm applies, right? So if we look at these assumptions here, right, this fourth one isn't, it's more about the analysis. It's not really when the algorithm applies or doesn't apply. The third assumption very much impacts when the algorithm can be applied. A, it only works when A is going to be S-sparse. You can't do it for general A. This one is important too, right? If I don't have a circuit for preparing B, then the algorithm just doesn't apply. So that's important. And the first one is also just to simplify the analysis, but you can generalize the algorithm to work even when you're not Hermitian and full rank. Okay, so there's some kind of tricks to do that. So the additional assumptions are just purely to make our pedagogical lives easier and to make the key ideas shine through. And so I'm just going to assume that, first of all, there's absolutely 0 error in preparing B. Okay, so you have a polynomial-sized quantum circuit, and it prepares exactly the state B you want, not some funny approximation. The second thing is that so far I assumed that the matrix A is not just S-sparse, but it's also Hermitian, right? So throughout I assume this. That can be relaxed, but now I'm going to strengthen the assumption. I'm going to assume that not only is it Hermitian, but it's PSD, meaning its eigenvalues are all non-negative real numbers. Okay, and this since we assumed that A inverse was, sorry, the infinity norm of A was precisely 1, this means that kappa of A will be 1 over lambda min of A, essentially. It'll be the inverse of the smallest eigenvalue. Okay? And number 3, I'm going to assume that all the eigenvalues, which I now know because I assumed that the norm of A was at most 1, was precisely 1, and it's PST, then I know all the eigenvalues lie between the smallest eigenvalue of A, of course. How did I write this? Lambda j, right? They're at most the smallest eigenvalue, they're at most 1, because that was my norm bound on my matrix. Require at most n bits to represent. Okay, and I'm not really going to tell you what A is, it's just some parameter that you can adjust as you want. Okay, and of course, the more n you want, the larger n gets, the worse your runtime is going to get. And intuitively, remember, this is going to be a huge problem for phase estimation. If you really want very high precision in n, phase estimation is going to struggle. And finally, the other simulation we're going to do, the other black box I'm using, is this Hamiltonian simulation. And we're going to assume that this simulation is done error-free. Okay, so whatever time I want, of course it costs me something to do the simulation, but I'm not going to assume any error in that simulation. Okay, so exercise 14 will just basically get you to confirm you understand points 2 and 3 and how the condition number simplifies to things involving lambda min in this case. So I've stated all the assumptions I need for the algorithm. Now I will state the algorithm, which requires only 5 sentences to write down. Okay, and it's going to follow the high-level sketch of what we did before, right? So eigenvalue surgery. Here it is, number 1. So first, we're going to prepare that state B, right? Remember aside, we had A x equals to B, right? And then we wanted to compute x equals to A inverse B. That was our goal, right? That's what we're aiming for. So I'm going to prepare B. Let me write B in terms of the eigenvectors again of the Hermitian operator that I have. Okay, so remember that we assumed over here that we can prepare that state efficiently. That's where I'm using that assumption. And this is going to be an eigenvalue of A, right? Eigenvector, sorry. So A psi j equals to lambda j psi j. I've just expanded this vector B in this eigenbasis. Okay, so that's the obvious thing I'm going to do to start with. And now, remember, I want to do this eigenvalue surgery, right? So I have these eigenvectors implicitly. And now I want to extract eigenvalues out so I can simulate this inverse map by inverting those eigenvalues one by one. So let's do that. How do we extract eigenvalues? Well, we apply quantum phase estimation. Okay, so on the unitary e to the I a with an n-qubit ancilla. Okay, and so remember, I'm assuming, here I'm going to use an assumption, right? I'm assuming that my phase will fit in n qubits, right? Here I put it n bits right here, right? So I know that, this, and since I'm assuming that the simulation is also going to be done perfectly, I know that phase estimation will work perfectly with certainty, and we'll put exactly all of these eigenvalues into the phase register. Okay? And in particular, what we'll get is, so I'm going to apply, quantum phase estimation, right, to B, which is quantum phase estimation applied to, just write out the definition to be explicit. So in superposition, I have these states. And what does it do? Right, it basically gives me the sum over j equals 1 to n. Eigenvectors, don't go anywhere. The beta j's, of course, don't go anywhere either. But what you'll get is this new register, which is it'll put in the phase, lambda j, and for technicality reasons, we'll stick in a 2 to the n in there. Okay. So we'll compute the phase. The red part is what's new in this step. And just to be formal, we are living in this space. The first register is n qubits, little n qubits. That holds the phase here. And the second register is capital N dimensional. Okay? Okay, so far, what I've done is I've started with my target vector B, and then I have extracted out the eigenvalues one by one, coherently using phase estimation. And now my goal was to invert the eigenvalues, right? So let me do that. Okay, so I'm going to sort of skip one step, which is in the previous preview, we first computed the kind of the function we wanted, and then we conditionally rotated an ancillary qubit and post-selected on that to kind of force f of lambda j to kind of show up, right? So I'm going to skip the step of explicitly showing that, I'm going to compute f of lambda j in another register. I'm just going to do that conditional rotation immediately, okay? Just for sanity, okay? So what we'll do is conditioned on, by the way, let me get rid of this taskbar so it's a bit cleaner. Okay, so conditioned on the first register, rotate a new single qubit ancilla, right? So what will we do? So again, I'll write all the new stuff in red. This looks the same, beta j. Here's my eigenvalue written perfectly by assumption. And now conditioned on this lambda j, I want to do a rotation on a new qubit, right? So I'm going to have a 0 and a 1, and the goal was 1 is going to store kind of what I really wanted to kick out as a phase, okay? So in particular, what I'm going to do is, what I really want to do, right, is ideally, I want to kick out 1 over lambda j, right? I want to invert this eigenvalue. So ideally, what I want to put here is 1 over lambda j, right? And then on the other side, I would put the square root of 1 minus 1 over lambda j squared, just to make things sum n squared to 1, right? Now there's a bit of a problem because I have no idea how small lambda j is, right? If lambda j was, say, 1 over 100, let's just say, then 1 over lambda j will be equal to 100, right? Which is, much bigger than 1. So there's no way this vector will be normalized, right? This number is just way too big. So I have to squish this number down so that it fits between 0 and 1, right? So that I have some hope of making this a unit vector. So what do I normalize by? Well, it turns out that all you have to do is multiply by the condition number of A. And I'll just let you convince yourself that indeed this is exercise 15, okay? Convince yourself that indeed if we divide through by the condition number of A, then you'll be guaranteed that this thing will be between 0 and 1. And then this will be a unit vector. And of course, this also means that here I need to add a k squared of A here. Okay, now this is a unit vector in the ancilla. Okay, for clarity, let me tell you the space this lives in. C2, tensor n. Okay, n qubits is the first register, this one. Second register was a capital N dimensional register. And the third one in red, right, this is this register here. It's just a single qubit. Okay? And now what I'll do is, I want to do post-selection, but before I do that, let me also just do some own computation of the garbage now. So in particular, this is my garbage here, in the sense that I don't need lambda j anymore. So I can run phase estimation in reverse. Okay, so run QPE inverse, or just dagger, it's unitary, right? And that will give me what? It will give me sum over all the beta j. And what's new is that this second register now will just be 0 to the n. So it's just going to reset that one, psi j, And I'm going to have all this stuff again. Lambda j squared, kappa squared, 0 plus 1 over kappa lambda j, 1. Okay? So I've reset this first register, so I'm just going to ignore it in the rest of the computation. It doesn't matter anymore. Okay, I could trace it out. And now remember the last step of the eigenvalue surgery was that, to complete this kind of reinsertion into the matrix, quote unquote, hand waving like crazy business, we wanted to measure this qubit and cross our fingers and hope that we get outcome 1, because then this term will die off and we'll have a 1 over lambda j injected in. Okay, so that's the last and final step. Measure this ancilla in the standard basis. Post-select on 1, and then you could discard this last register. Okay, so once I've post-selected on 1, I can throw that register away at this point. And so what do I get? Well, then I get the sum over j equals to 1 up to n of beta j of 1 over, so here's the term I just injected, right? Kappa of a times psi j, right? And what is this thing? Well, so I'm going to play a little trick here. Let's be very careful, right? Let's stare at this for a second, right? What did I want to prepare? What I claim that this is equivalent basically to j equals 1 up to n, beta j, and just 1 over lambda j, right? That the kappa will disappear. And if this is correct, this is proportional to what I wanted, which was A inverse times B. Okay? So why can I do this? Where did the kappa go, right? Well, and so by the way, this is why, okay, we'll see why in a second, but lambda, so first pause the video and see if you can figure it out. Yeah? Take a moment. So if you've unpaused, lambda j depends on the sum, right? There's a j here, right? Kappa does not depend on j, right? So this is a global constant, right? I could remove it. If I want to, I can take this kappa here, and I can instead write it over here. That's just fine, right? Exact same thing. But remember that a quantum state, basically, you're not going to detect any sort of global phase, right? And so we can basically ignore this 1 over kappa term, right? Because it's global. And indeed, you might wonder why I kind of took this big hammer and I divided through by this condition number. Maybe I could have tried to do something a bit more nuanced that would depend on the specific j in question. And one of the reasons is because here, we could very easily, if I pick k to just be this fixed quantity, the condition number, which does not depend on j, then in this step, I can eliminate this term. The kappa just kind of disappears. It just goes into a constant, a proportionality constant. And then I get exactly what I wanted, right? Which is, 1 over the eigenvalue times the eigenvector. And let me be clear that, of course, this is not necessarily normalized, and that's why this thing will just be proportional to the right answer, right? It's not exactly the right answer, it'll be proportional, right? There was a post-selection, right, for example, and I haven't renormalized after I post-selected, right? Here I projected onto the 1, I killed off part of the state. I haven't renormalized since then, right? So this will not, well, I've also thrown this out, right? And so, of course, the output that the algorithm will give you will not necessarily be this thing. Right? It's proportional to this. And you won't get that, of course, you'll get the renormalized version of this, right? So the algorithm gives you what? It gives you A inverse of B, right, over its norm. It's got to give you a unit vector, right? So let's be very clear. You get something that's implicitly normalized, of course. So I want to do that here, but let me remind you here that well, sorry, not let me point out exercise number 18, which is, you might be wondering, right, where's the bottleneck, in some sense, in applying this eigenvalue surgery? So in particular, I mean, let's assume that, all the eigenvalues are nice, they all have just n bits of precision, so phase estimation is not going to be a problem. I can always extract them properly in this previous, I guess that was technically step 2 for us, right? I can always extract the phases. So where's the bottleneck in whether or not this eigenvalue surgery is really going to work? Well, what did we do? We did this conditional rotation depending on lambda j. That's fine, I can always do that. The only kind of funny part is this step here, right? After I did the rotation, I then measured and crossed my fingers and hoped that I got outcome 1, right? So the key question is, what is the probability that you're going to indeed see 1, right? Because if that's very unlikely, this technique is not going to work for you, right? You're going to have to repeat this whole procedure many, many times until you see a 1. Bad news, right? So instead, you want this weight to be sufficiently large, right? Say ideally a 1 over polynomial or something like this, right? So that you'll have to repeat the whole process a poly number of times until you see a 1 on expectation. And I'll let you figure this out on your own. Like, you can just take this vector and compute basically, if you kind of cut out this part, what is the norm of the remaining vector? That will be your probability of seeing that 1. What is that, right? And so this is exercise 18. Prove in step 5 that the probability of post-selecting on 1 is at least 1 over kappa squared of A. Okay? So if you're wondering where in the world is this condition number going to annoy us, right? Well, here's where it annoys us, basically, right? The probability of this post-selection step working scales with 1 over the condition number squared. So naively, you would have to repeat this entire process, right? Steps 1 to 4, and then 5 on the order of kappa squared times, so that you're, with high probability, you're guaranteed to get the outcome 1. Okay, so that's why you're going to see kappa squared or kappa showing up in the final runtime of the algorithm. And again, this is completely expected. Like classically, the bigger kappa gets, the worse your inversion algorithms get, right? This is completely normal. By the way, you can technically, this is naively, you would have to repeat this kappa squared times. If you use a technique known as amplitude amplification, you could reduce this just to kappa times overhead. But I won't say more about that here. Okay, so that's the basic algorithm. Let me just very briefly remind you how it went. Right, just to recap, we first prepared B using our assumed oracle for it. We ran quantum phase estimation on e to the I of our desired matrix A to extract the eigenvalues of A and put them into an ancilla register. We then conditioned on this register, rotated a new single qubit ancilla that scales so that the weight on 1 would scale like 1 over lambda j, which was kind of the quantity I wanted to inject. We cleaned up the garbage, and so I removed the lambda j I had computed. And finally, I measured this last register and post-select on 1 with the hope of kicking out this 1 over lambda j amplitude. And then I'll get basically something proportional to what I want, A inverse B. Good. So let me tell you just a bit about runtime. Okay. So the runtime, of course, I can't give you it exactly in the sense that, for example, we assumed a black box to prepare the state B. We don't know what the cost of that is a priori. So let's just give that a name. Let's suppose that TB is the number of gates, say from some fixed universal 1 and 2 qubit gate set, to prepare B. Okay, so obviously my final cost will scale with TB. So the total runtime is what? Well, so I'm going to again throw out all like the slower growing terms. So O tilde. So what's going to happen? First, we have steps 1 to 5, and we'll have to repeat these some number of times that naively scales with 1 over kappa squared. With amplitude amplification, we can improve this to 1 over kappa. Okay, so the total number of iterations will be kappa of a if we're a bit more clever, right? And I won't talk about the amplitude amplification here again. And now what is the cost per iteration? Well, what did we do? First we prepared B, so obviously I have to pay for preparing B. Okay. And then the other thing I essentially had to do is I had to run Hamiltonian simulation to do the phase estimation, right? That was kind of the major subroutine, if you will. So let's account for that cost. Sorry, not t squared, but t s squared log n. And here I'm just literally plugging in the runtime from the sparse Hamiltonian simulation I pointed out earlier. Okay, so this is essentially Hamiltonian simulation time. These will be the dominant terms. Okay. And now the question is, let me remind you, of course, that this t business, right? This is the time for simulation, right? For simulation, meaning we computed e to the iht, right? And remember that this t depended very strongly on the number of bits of precision we wanted to extract from quantum phase estimation. Okay, so if you wanted n bits of precision, so if you want n bits of precision from quantum phase estimation, so you need t to scale like 2 to the n, exponentially in n. Okay. And certainly, at least this is true when we assume that your eigenvalue, your phase can be written exactly in n bits. Okay. Now, let's just kind of rephrase all of this in our terms, right? So, so the total runtime, if I want, I can take this basically, and I could replace it with a 2 to the little n here if I want, because that's kind of going to be the upper bound on the Hamiltonian simulation time. And now, what do we have in our setting, right? Well, what parameters can I plug in to make this thing polynomial in the number of qubits, which is log n, right? Well, so remember that a is n by n, right? That's the dimension. So the number of qubits is therefore log n on that order. Okay, so therefore, sorry, there's no if here yet. If n is, so if the number of bits of precision you need is logarithmic in the number of qubits, okay, so log n, right? So in other words, remember, log a number of qubits precision means inverse polynomial additive error, which is exactly what we expect for BQP, okay? This is technically, if I expand this out, this is technically the log of the dimension n, right? Okay, so in this case, phase estimation only gives you a 1 over poly additive error, and that's fine. Then we get runtime O tilde, kappa basically, times preparing B, s squared, and then here we'll have an extra factor of the log, right? Okay, so if you know for your application, right, that it suffices, to compute this operator function like A inverse, if it suffices for you to worry about just, log in the number of qubits, bits of precision, right, then the algorithm will run in polynomial time in the number of qubits, right, which is exponentially faster than the full dimension n, right, because it's polylog in capital N. Of course, the other terms also have to be polylog, right, in order for this full thing to be polylog, right? So, the sparsity has to scale like polylog. The time to prepare B should also be polylog in the dimension. And finally, the condition number, of course, can't be too big either, right? So if all those quantities are polylog, then the full algorithm runs in time polylog, meaning it beats, well, again, it's much faster than classically inverting the system, right? Because then you don't have to write the full system out. But again, we're not solving the same task as classically, right? I'm not producing the full solution vector. I'm giving you a quantum state which has the solution vector kind of in superposition. Okay, so therefore, for when the condition number of A, T, B, S are in polylog, this is exponentially faster than a classical algorithm. And let me be clear, it's not a fair comparison, right? We're saying that explicitly solves the system. Okay, that writes out the full solution. Okay, so this is kind of the basic premise of the runtime analysis. Of course, there's more you can say. So, a priori, you have no idea how many bits of precision you need for the eigenvalues, of course. But you can make things, you can introduce some error, you can relax the analysis, right? And you'll get kind of a similar runtime. You might, maybe in the notes, it's a bit stated in a bit more detail what you'll get if you want to kind of relax this assumption of, you know exactly how many bits you need to represent each eigenvalue, right? And then this runtime will get slightly worse, but roughly speaking, it's going to look something like this. Okay, so do refer to the notes for that part. And let's see, how are we doing for time? Maybe in the remaining time. So there's a little bit on optimality in the notes. And I'll refer you to read that, but maybe I'm going to ask whether or not, in some sense, you can do any better for this task, right? By which I mean, is there some way, right, to kind of simulate, well, okay, you have to be careful how you specify these things, right? Because the output of the algorithm is a quantum state. So what does it mean for a classical algorithm to simulate doing that, right? I mean, obviously it can't output a quantum state, right? So, and that's kind of the discussion I've sort of skipped on optimality. So maybe let me just not say the words optimality anymore and refer you to the course notes for that. There's a paragraph on page 8 for that. Let me instead close with the final section, which will cover the kind of the last 2 pages of the notes, which is a BQP-complete problem. And so all we're really saying here is something very nice and elegant, which is that it's kind of no accident that we can solve linear systems in this sense, right, on a quantum computer, because it turns out that this task of matrix inversion, if you could do that, then you could simulate anything else in BQP. Okay, any other polynomial time quantum computation can always be reduced to some instance of matrix inversion. Okay. So that's what I want to discuss. And to do this, again, we're going to start with the formal definition. What do I mean by matrix inversion, right, in this particular setting, right? I have to set the conditions or the assumptions just right so that a quantum computer can, of course, do it, right? And so let's do definition 21. And this is going to be the matrix inversion problem, or just MI for short. And so what we'll say is that the promise problem, remember BQP is a class of promise problems, MI equals to A yes, A no, A invalid, is defined as follows. So what's your input? First you get a constant sparse invertible Hermitian matrix A. Okay, so it's an n by n matrix, capital N, and it has the property that the eigenvalues of A are all between identity, and they're between kappa inverse of A. Okay, and sorry, let me be clear that we also need the condition number. Remember, in order to run the linear systems algorithm, it's got to be polylog in the dimension, right? So that's going to show up somewhere here. polylog n. And okay, and we want A to be row computable, right? So this is just from the definition of being a sparse matrix. So I guess I didn't need to explicitly state this again, right? Not only is the matrix sparse, but you know, it's row computable. So you give me the row index, I tell you where those constant number of entries which are non-zero in that row. Okay, so that's the input, and you'll probably notice immediately right away that these are exactly the types of conditions we needed to run that eigenvalue surgery trick and to invert a matrix quantumly. So that's intuitively why we're going to be able to run matrix inversion in BQP, which is one part of BQP completeness. And what is the output? Well, we're basically going to ask for what we did just now, right? Which is, imagine you want to invert the matrix A on some start vector. So let's just say all zeros. That's kind of a trivial one. And so let's give this a name. It's going to be the vector proportional to this, of course. And let's suppose it's a unit vector, right, my x tilde. And pi is just going to project onto 1. It's going to be the accepting projector, basically. So it's just a projector that's on a single qubit and onto the first qubit of x. Right? Then we have three conditions, right? Completeness, soundness. If, so what are you supposed to do in this game? You're supposed to imagine you start with a zero vector, apply an A inverse, right? And then measure the resulting vector x tilde, just the first qubit. And I want you to look at, what's the probability of getting 1 when you measure that first qubit of kind of the solution vector? That's what this is saying. So if I measure, that's my measurement pi, the solution vector to this linear system, right? And it turns out that it has probability at least 2/3 of outputting 1 on that first qubit, then I want you to output yes. Soundness, right? So if this thing is now at most 1/3, you're supposed to output no. And in the invalid case, you could do whatever you want, right? So question mark, question mark, question mark. So you can output yes or no with any probability in any way you like. Okay, so if you stare at this, it should be clear to you that this problem is certainly in BQP, right? Because it's just a special case of the linear systems algorithm we just outlined, right? And that's, by the way, again, why I needed all these funny conditions like sparsity and so forth, right? Because then we can run the algorithm. And so kind of the non-trivial part now, given the previous algorithm, of course, is theorem 22, which is that not only is this problem matrix inversion in BQP, but it's actually BQP complete. Meaning any problem, in any computation in BQP can always be embedded into an instance of matrix inversion. And this is going to be under polytime, many one reductions. Okay, so that's what we'll sketch in the rest of this lecture, which is how do you show that it's BQP hard? Okay, and there are a number of details which I won't be able to explicitly state in this lecture, so there are a bunch of exercises to kind of go along with this discussion, but I'll basically give you the high-level sketch of how you do this embedding and what's the main idea, right? Why should this even work? Okay. So let me be clear that so MA in BQP follows by the previous algorithm, so I'm not going to write that again, obviously. So now we sketch BQP hardness. Okay, so what that means is that I want to take a circuit, V, which is just a BQP computation, right? It's uniformly generated, but for this discussion, it's just a circuit. So it'll be a BQP circuit on n qubits. Okay. And m, which is just the number of qubits, is its polynomial in n, right? So it's just the definition of BQP. And we're going to define, n is going to be logarithmic in capital N, which is a dimension, right? Just to be consistent with the previous notation from the previous section. Okay, so that's kind of the input. We start with a BQP circuit. And what do? We construct a matrix A for Mi as follows. Right, so the main idea is that, if the BQP circuit V accepted, right, when we measure it with high probability, then it should be true that we're in the S case here, right? That when I compute the solution to this linear system, there it goes. Nope, let's not do that. Then, my probability on the solution vector to the inverted system, measuring a 1 in the first register should be large, okay? And conversely, if the BQP circuit was going to reject, then here in my solution vector to my linear system, it should output 1 with low probability. That's what we're going for, right, in a many one Turing reduction, CARP reduction. Okay, so here's idea 1. It doesn't quite work. But let's see what's going to happen, yeah? It almost works, okay? So let me define a U in this fashion, okay? It's a very elegant trick. So remember I had m time steps in V. And what it's going to do is it's going to say, okay, if I'm in time step t and I jump to time step t plus 1, right, that's intuitively what this says. Oh, there's my t plus 1. Then, of course, then I want to apply which gate? Well, I want to apply the t plus first gate in the sequence, right? That's just the sequence up here. So that's really what it's saying, right? Whenever I'm in time t, I jump to t plus 1, and I apply the next gate in the sequence to t plus first. And I'm going to also put in this thing here. Whoops. And what this thing is going to do is it's going to kind of do the opposite, right? So from times 0 to m minus 1, this thing's going to apply these gates v1 through vm. And then this second part is going to, when I go from the next time steps m to 2m minus 1, it's going to start inverting them all. Okay? So when I started whatever the current time t is, and then I go to t plus 1 mod 2m, then I want to invert that gate 2m minus t. Okay, so it's like we build the circuit, then we start undoing it. So for clarity, this is a unitary operator. It acts on log m qubits, tensor C2 n qubits. Okay. So I'm just defining this unitary. Okay, and by the way, it's not obvious at all that maybe this is a unitary at all, right? So equation 23 asks you to show that indeed U is unitary. So I encourage you to do that. Let us do equation 24 together, because that will be important for understanding what in the world this is talking about. And the claim is that if I do u to the power m, and let me highlight this m, right? So it's not just u, but it's u to the power m of 0, logarithmically many zeros, and just 0 to the n here, right? Then what I'll get is 0 to the log m again. But what will change is it'll have the effect of applying the circuit V, right, from my BQP computation to my state of all zeros. So, and by the way, this is what you want, right? This is going to be, what the BQP circuit would do, right? It starts with all zeros, and then it runs a circuit. Okay, so why is this true? Okay, so by the way, why is this register only log m qubits? Well, it's because the number of time steps I ever want to represent, right, over here, right, there are m time steps, so I only need log m qubits to represent those. Okay, so what is this doing? Well, I mean, let's just kind of do it step by step, right? Imagine I did u times, 0 times 0, right? What does that do? And here, of course, I'm just looking at this, right? Let's just do one step at a time, right? Whenever you're not sure what in the world something is doing in a paper like this, start from the beginning. Do the base case, right? So what do we get? Well, the first register, you have the sum, and when t equals to 0, you're going to have this inner product with 0, right? So what's going to happen is that I'm going to get a 1 coming out, right? Because when t is 0, then a 1 will show up here. And maybe I should write this explicitly, right, just for the first time. There it goes. Okay. So I have, 0 on my end, right? Sorry. So basically what we have is that I have 0 and then 0, right? And what we're multiplying by is 1 tensor 0 tensor v1, right? I'm not going to bother writing the other terms in the sum here. Where's my mouse cursor? It's disappeared. Don't you love playing Find Your Mouse Cursor? I don't know. Okay, well, anyway, it's gone somewhere. But anyway, I'm not going to write the other terms in the sum down because, then t is bigger than 0, and so my inner product with my time register here is going to be 0. So those are going to disappear. Okay, and likewise here, these times start at m, right? So whenever I take the inner product again with this time register down here, those terms are going to disappear because I only have time 0 right now. Okay? And so what happens here? Well, the time register is going to go to 1, right? If I just work that out. Because, well, technically speaking, let's just work it all out once for completeness, right? And then it'll be v times 0 by the properties of the tensor product, right? And so that's just equal to 1 times v0. Okay, sorry, v1, let's be clear. Okay, so the first gate comes out. And so intuitively, in general, this is exactly the kind of thing that's going to happen, right? If I apply it once, it applies the first gate. If I apply u again, right, now the time register reads 1, right? So what it's going to do is that it's going to rip out the next gate in the sequence. It's going to apply v2 now, okay? And so if I apply more generally, so let's do it, if I do u0 then it's going to be what? It's going to be u times 1 v1 of 0. That's what we just did. And now if I apply u again, it's going to update the time counter to 2, and then it's going to apply the second gate in the sequence, right? It's going to look like this. So my lovely okay, there we go. Okay, so therefore, you can sort of see that if I do this m times now, you're going to get, applied to 0, 0, you're going to get what we said, which is, why did it go to 0? I think that's a typo. Yeah, sorry, that's a typo in the notes. It should be m, right? So it should be m here. In the notes it says 0, but that's wrong. So let me just correct that. Okay, so there should be m in the first register, and then you should have the full circuit, Vm to V1, 0. Okay. So in other words, if you apply this unitary I defined, this funny thing, to the power m, oh, look, my mouse cursor is back. Oh, it's gone again. All right. Well, if you apply u to the power m, then it has the effect of simulating, given the start state of all zeros, of simulating all the gates v1 through vm. Okay? All right, so that's the action of this u I defined up here. Right, I defined this u, and so that's the action of u when you raise it to power m. And here it's going to do the opposite, right? As you start counting from time step, basically m plus 1, or let's say m up to 2m minus 1, it's going to start undoing these gates one by one, right? So every time you kind of go through from time t equals to 0 up to 2m minus 1, you're going to re-arrive at your start state of 0, 0. It's going to kind of do the circuit, and it's going to undo it. It's going to do it, it's going to undo it, right? As the exponent kind of goes up, basically. Okay, so that's exercise number 25, which says that, basically, remember exercise 25, not remember, but let me tell you, says that for what k is u to the k 0, 0 to the n equal to 0, 0 to the n. Right, so obviously when k is 0, this is true. But because the u has this thing of, first it builds up the circuit V and then undoes it, every time it kind of goes through that process, it's going to reset back to all zeros. Okay? And that's going to be important in a second. Okay? Okay, so that's just a matrix U, and it's just a very nice matrix because if I raise this thing to higher and higher powers, right, it implements more and more of my desired computation V, right, my BQP computation. So why in the world, though, would I write my computation this way, right? So that raising U to a certain power will implement, all the time steps up to that power. So the reason why is, we're not done yet, right? We still need to somehow embed. We still need to, ultimately the goal is to put everything into a matrix which we're going to invert, right? And the inverse of a matrix in general is a pretty nasty thing to deal with, right? But there is one very nice tool, right? Which is Taylor series expansions, right? We can always write the matrix inverse, under certain assumptions on the eigenvalues, we can write it very nicely in terms of a power series of terms that will scale like some quantity to some power, right? And that's intuitively why we wanted to write the action of V into some matrix U, so that when you start raising U to higher and higher powers, it's going to start applying more and more of the matrix V. Let me make this all formal now, okay? So the question is, need to embed U in a matrix A, right, such that A inverse captures U slash V, right? Because U ultimately captures V. Okay, so what's the basic idea, right? Well, let's again take inspiration from the classical setting. So recall this Maclaurin series expansion, right, which says that if I have 1 minus 1 over x, right, so this is an inverse, right, it's 1 minus x inverse, right, it's an inverse function. This has this cute infinite series, right? Okay, you probably learned this in high school, latest university, and this holds whenever the absolute value of this x is strictly smaller than 1. Let's be clear, right? Obviously, if x is 1, then this is not even defined because then the denominator is 0. Okay, so now what we'll do is we'll simulate this Taylor series expansion, which holds, whenever you're in this range, right? We'll simulate it, we'll use it to, simulate the inverse of a matrix instead of just a scalar, right? We'll treat it as an operator function. So that's the main trick. That's the main trick of how I'm going to map an inverse of a matrix to something that scales like powers of a matrix, okay? That's the main bridge. Okay, so identity minus U inverse, right, equals this thing. Just literally, plugging in this definition, right? This is operator functions at work. Okay, technically speaking, of course, what I've done is not correct. Well, why is that? Well, this is exercise 26, right? To apply in order for this Taylor series to converge, right, you have to have this property, and in general, the eigenvalues of U all lie in the unit circle, right? So in other words, this, x here, which denotes the eigenvalues of U for an operator function, those eigenvalues in absolute value are all exactly 1, actually, right? So they totally fail this condition. But regardless, this idea doesn't quite work yet, but we can massage this to make it work in a second. Okay, but for now, pedagogically speaking, this is the idea, right? We're going to simulate, this inverse using this Taylor series expansion. So my goal was to define a matrix that I'm going to invert, and that matrix should depend on u. So here's a matrix that depends on u, identity minus u, and, lucky me, there's a -1 in the exponent, right? It's an inversion problem. So I'm going to call this A, okay? Not the full thing, just identity minus u. So let me be clear, A is identity minus u, okay? And, okay, so once I define A to be this, I'm going to think of this as, the solution then to the system, remember, will be A inverse, just by definition. So I'm going to come up with, there are two things I have to specify for the problem, right? I have to specify A, and then I have to specify, B, which for us is just, actually, no, we already have B. I take that back. It's just all zeros, right? So in the matrix inversion problem, I'll go to scrolling again. Right? What do I have to tell you? I need to basically tell you A, right? And A has to satisfy all these conditions, which I'm not going to go into in this lecture, obviously, in the interest of time. You could always refer to a bit to the lecture notes for some more details, and also more so to the original papers on this topic. But this target vector is all zeros in this case, right? That's fixed. So I've defined A, and therefore I can now talk about x tilde, which is A inverse of 0, right? So what is A inverse of tilde, of all zeros? How many zeros are there? Technically log m plus n. What is this equal to? Well, what is this equal to? Well, by definition, right? By definition of this Taylor series operator function, assuming we forget about this problem where we don't satisfy this criteria for convergence, right? What you're going to get is, let's just plug it in, this thing. The sum over L equals 0 up to infinity, u to the power L. Again, u for me was this funny, nasty matrix. Well, it's not nasty. Actually, it's a very nice matrix. I take it back. I love this matrix, right? So this matrix here, u. Where did I put this thing? Good. U to the L, and then you have 0 to the log m technically, and then 0 to the n here. And so that's what it is if you expand the Taylor series, right? And that's very nice because remember, if I raise m to the right, u to the right power, then I get exactly what I want. I get kind of the full circuit applied to all zeros. But not only that, right? What's going to happen technically is that, remember, it's going to do this funny thing where it's going to kind of keep applying the circuit forwards and backwards, right? Because we had two parts, right? I have an infinite series, right? So the exponent's going to keep growing. But the way I set this up is that, you go from 0 to m, it applies the circuit forwards. You go from m to 2m, it reverses the circuit. And then, you kind of rinse and repeat this thing as u goes to higher and higher powers. And these things are always done mod 2m. Okay. So basically the point is that this term here, if you kind of expand this thing out, you're going to see the main terms, you're going to see the same terms over and over again infinitely often, right? So you're going to get something that looks like 0 to the 0 to the n plus 1 times v1 to the 0 to the n plus dot 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 plus m times vm v1 times 0 to the n. Okay? So you'll see these terms kind of infinitely often, but ultimately you'll be proportional to this thing. Okay, you'll just collect like terms. Sorry, I was slightly confused about something. Yeah, okay, good, yeah. So notice how when you get to this thing, it's going to, when you hit 2m, this will reset the time register back to 0. Right, that was confusing me for a second. Good. Okay, so even though this is an infinite series, because we defined u so that when you raise it to high enough powers, it kind of undoes itself. Now this is really nice, because then I'll just see the same terms showing up over and over again in this infinite expansion. And I claim it'll look essentially like this. This is technically not entirely accurate, because not all the terms will be perfectly equally weighted. I'll let you think about that. This is equation 27. Okay, but for now, let's just assume that everything is perfectly equally weighted. So I haven't bothered writing down weights on each of these terms. Okay? So therefore, what this means basically is that you'll notice how each of these are orthogonal unit vectors, right? They're orthogonal because, their time registers are all distinct, right? So they're certainly orthogonal. And they're all unit vectors because it's just unit vector times some unitary, say v1. Therefore, my state x tilde, right, up to kind of the fudging I've done, even though it's an infinite series, technically speaking, it's just this state, right? You have to normalize it because there are m+1 steps. But it literally just looks like this. 0, 0 to the m, plus 1, v, 0 to the n, sorry, this is n, plus dot dot dot, plus m, vm dot v1, 1, 0 to the n. Okay? So in other words, if I now measure this first register, where'd my time register? Oh yeah, okay. So in principle, if I can prepare this inverted state, A inverse of all zeros, right? The state I get, right, when I unroll kind of this Taylor series expansion and collect like terms, I'll get essentially this state, up to some minor fudging. And now I'm in very good condition, right? Because, most of these terms are no good for me, right? But this term is very good for me, right? If I measure the first register, right, and I happen to get the value m, then I post-select onto this state, which is exactly what the BQP competition would have done. All zeros, gates 1 through m. And that's the name of the game, right? What are the odds of that post-selection happening? Well, all the terms are equally weighted, and that weight scales like 1 over root m, so it's 1 over m when you square it. Okay? So with probability basically 1 over m, right, we can post-select on m and extract the answer to the BQP computation vm dot 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 v1 0 to the n. Okay? Bingo. And that's exactly what we wanted to basically show. Okay, I mean, we have to be a little bit more formal, but that's the basic idea here, right? That's the intuition. So I defined this funny operator u, and then I defined a to be identity minus u, so that if I invert a, right, I have to do identity minus u because the Taylor series expansion is for 1 minus x. So identity minus u, if you invert this, you'll get this infinite series, and that thing will just kind of repeat itself. So ultimately, the solution vector will look like this. And the answer to our BQP computation is hiding in one of those m terms, basically, m+1 terms. So let me be slightly more formal, right? What we can show is that when you go through the formal analysis, so if V, the BQP computation, is a yes instance, meaning that it was going to accept with probably at least 2/3 when you measure its first bit, then if I take this x tilde, this guy over here, and I measure his first qubit pi, 1, 1 on first qubit, I guess we're cheating a little bit, right? It's not really on the first qubit. It's the first qubit of the second register, technically. But these are just technicalities, right? It's this second register that holds the answer, right? So let's assume the first qubit holds the answer to that computation, right? Then this quantity here will be at least 2/3 was what you get out of BQP, but now I have a post-selection probability, right? I'm only going to get this answer with probably 1 over m. The rest of the time I'm going to get these funny answers, so I have to account for that. Here I'll get a 1 over m plus 1 additional loss, which is fine. All right, then very similar. And now I'll get 1/3 and same deal. Okay? And this is exactly what I wanted because now I have a linear system where if I could invert it and prepare kind of this solution state x tilde, which is a inverse of all zeros, then measuring the first qubit of that will be inverse polynomially separated. So let me go back up, remind you what that looks like. was it? Definition right over here, right? So technically I wanted it so that when you invert the matrix, the probabilities are at least 2/3 or 1/3. But we can certainly boost this to be, what we got was not 2/3, 1/3. If you go back here, right? Go back here, and you'll see that we don't get that. We get two values. It's because you lose in the post-selection step, but they're still inverse polynomially separated. And that's generally speaking fine. If they're inverse polynomially separated, I can make, instead of 2/3, 1/3, remember I could do error reduction for BQP to make this thing exponentially close to 1, so essentially like 1, and make this thing essentially exponentially smaller than 1, exponentially close to 0, right? So then this term will be roughly 1 over n plus 1, and this term will be roughly 0 times 1 over n plus 1, so 0. And then indeed, that'll give you the 2/3, 1/3 separation you want. Okay, now this is almost what we want, right? I've given you kind of the basic vanilla version because it has all the intuition, and now we just have to, fix some minor things, right? And I won't go through all of them. There are a bunch of exercises in the notes, but in the interest of time, I'll maybe just focus on one thing in particular that I do want to mention. So let me first mention some things that we haven't done, right? So in the matrix inversion problem, the matrix A had to be sparse, right? Okay, so we have to double check that the matrix A I have constructed here indeed is sparse. Okay, and if not, that has to be fixed, of course. I've sort of already talked about this, but we wanted, I'm just following the notes here, completeness, soundness, 2/3 versus 1/3, right? Whereas in the plain vanilla version here, I did not get that. I had this 1 over n plus 1 factor, but this we can fix, like I said, using error reduction. And 3, we also need A to be invertible with these bounds on the condition number, right? Otherwise, we cannot do the inversion correctly, or efficiently, I should say. Okay. And so actually it turns out that exercise 29, A is indeed going to be sparse, so that you get for free. Exercise 30 is what I've already outlined. How can you boost these probabilities? Well, use error reduction for BQP. And now, the one I just want to spend just a minute or two talking about is this last one. Is A necessarily invertible? Well, how did I define A, right? Well, actually, maybe I shouldn't scroll up and down because it's being finicky again. So recall that A was equal to identity minus U, right? And what if U is, say, identity, right? A unit is a unitary, so imagine U is identity, right? Well, then I get the 0 operator, which is clearly not invertible. So in general, A is not invertible, right? And intuitively, what's going on is we're ruining this. Remember, I said we slightly cheated here, right? This Taylor series expansion essentially only holds when the value of x has a norm smaller than 1. But in a unitary matrix, all the eigenvalues have norm exactly 1, right? So you kind of have to squish this a little bit so that its eigenvalues are not quite on the unit circle, but something a bit smaller so that identity minus that can never go to 0. It's a basic intuition, right? So the first thing you might try and do to fix number 3, exercise 33, is maybe you could define I not as U, that's too big, the eigenvalues are too big, but let's just say you put in a half, you scale them down, right? So the norm of everything on U is not on the unit circle, it's like divide by 2. And what you can show is that indeed this is really nice because it will also make the condition number constant, right? That's very good. But this still doesn't work. Okay, there's still going to be another catch. And I'm not going to tell you what it is. I'll let you figure that out in the exercise. So that's kind of the most naive thing you would do. But it turns out, we shouldn't throw out this idea entirely. If we just change this to be a little bit more clever, rather than a constant, we can make this idea work. So the solution to get this number 3 to be correct, that A will be invertible, is you instead set A to be identity minus and U, and now what I do is I do e to the minus 1 over m. So the scaling factor now is some exponential function that scales with m now, the number of steps in my BQP computation. Okay, and it turns out then, in exercise 34, you will show that the condition number of this A now is good. It's order m. Okay. And A will be invertible. This is kind of obvious, right? Because the eigenvalues here are 1, right? And the eigenvalues here are all going to have norm, whatever this thing is, right? So 1 minus something of that norm can never go to 0 intuitively. And now, of course, you have to rerun the full analysis we did before to make sure that we get the right completeness soundness gap, and this you can do. Okay. That's basically all I want to say for this lecture. There's a little bit more in the notes that talk about, what happens if A is not Hermitian? How do you make it Hermitian? There's a little cute embedding trick you can do. Again, in the interest of time, let me not go there. And maybe now is a good place to close and just review kind of what we've done in this lecture, right? So first, let me just review what we did in this section, right? We showed that it's no surprise in some sense that quantum computers can invert matrices in this very specifically defined way of producing a superposition over the entries of a solution vector to a linear system, right? So we defined this matrix inversion problem, which is right over here, right? So given a matrix A which satisfied some conditions like sparsity so that we can simulate it on a quantum computer, computing the solution to the system where the target vector is all zeros, not only can a quantum computer do that, not only is that in BQP, right, for the decision version, but actually any computation in BQP, we showed how to reduce it to a matrix A whose inverse will give you kind of the answer to your computation. And the basic way we did that, and I really want to stress this because we're going to see this come up again, is this idea of coupling kind of a clock register with gates in the circuit V, right? So that when you go from t to t plus 1, you apply the t plus first gate. This will come up again when we talk about the quantum Cook-Levin theorem. Okay, so it's a really nice construction. The idea dates back to the 80s to Richard Feynman, right? But here, of course, it's used in a slightly different way. And so basically, you take this unitary, right, which couples a clock register with the individual gates, and the way you connect it to the inverse of some matrix is via the Taylor series expansion, right? And that's how you can embed an arbitrary quantum computation in some sense into computing the inverse of some matrix, right, which a priori seems a bit odd. Okay, so that's the full lecture, right? We started by talking about this very broad idea of quantum eigenvalue surgery where you remove the eigenvalues of a matrix, you apply some classical post-processing, and then you kind of stuff them back in. And this is also that you can apply kind of some function f of a matrix to some target state. And then we showed how to apply that general framework in the specific setting where the operator function is the inverse, f of x equals to 1 over x, right? Because we want to invert a matrix in our case. And we gave the quantum algorithm for that. And finally, of course, we showed that the task that problem is solving, like this inversion problem, is complete for BQP. Okay, so any quantum computation that runs in polynomial time, you could always reduce it to an instance of this matrix inversion problem, again, properly defined with the proper assumptions in place. Okay? Good. So that is the lecture. Again, assignment 2 is due tomorrow. Other than that, I wish you a great week. And as always, please stay healthy.